So today we will see how to perform Abacus standard analysis and Abacus explicit analysis, and what are the difference and what are the similarities. So you can perform any analysis by both of the method, but Abacus explicit is called conditionally stable. So conditionally stable means there are some certain parameters that you need to select, and you also need to cross check that whether it is correct or not. So first I am going to create a geometry of a notch round tensile bar. So here it has, and the notch has a radius of 3 mm, and the cross sectional area diameter is 10 mm, that is it is a 5 mm of this distance. So it is in axisymmetric mode. Second, I have already given property such as density Abacus standard. Second, Pascal's, this is stresses or true stresses of the material after the yield point. Now section manager creates a, you will see the change in color, that means now assembly, and this is the main part where you create a step. There are a lot of steps, as you can see: static risk, general, mass diffusion, heat transfer, geostatic, explicit, implicit, etc. So we will see explicit and general. Implicit is also similar to general, but it has more options. So we will see the mostly easier one, that is general. So here it has a time period of 1. We will give a non-linear geometry on incrementation. It is supposed to be 10 times the initial time, 10 times lesser than the initial time. You can change these values to stabilize your calculations. Initially just keep these values. If it doesn't work or doesn't this method, I have not used, but I think we can also use symmetric unsymmetric type of matrix storage. People have also been used when there is no convergence of the solution, but here we will keep it default. So first you select this. If it doesn't convert, you can do this automatic stabilization by using this use damping factors. So we will keep it. Now the field output, every increment, you can make it every increment or evenly spaced time intervals. I will keep it default. Now there is no interaction. Load, we will assign it boundary conditions. simple displacement, no displacement in u2 direction, also constraint in the u1 direction, and we will displace this upper section like in the tensile test. So here it has amplitude is ramp, it is automatically selected in case of Abacus standard solver. So the step here we have selected standard step, that means the boundaries will increase according to this general step. Now the meshing. You can also create different types of meshing according to any kind of research paper if you follow. I will create a simple meshing here with a simple geometry. So basically what we do, we make meshing where we need stress calculation, we need finer meshing, and otherwise coarse meshing. Now we can assign section control to this structured it is only a meshing rule that you define to make your meshes more converge to the areas with high stress gradient such as notches. And this is the most important part, that is assign your element type. Standard linear, that is CX4R, that is for axisymmetric. You can either use reduced integration or full integration scheme. Reduced integration scheme are used where we have failure and we don't need additional stiffness. So we will keep it CX4R, and this section here highlights if the meshing has any poor element, or so as you can see there it has a poor element, that means it will give erroneous result with errors because elements shapes are very poor in this region. So we will delete this. We will again create. So initially what was the problem? We didn't created a symmetrical shape. That is why the element shapes were poor. Now we will create more symmetric shape. What we are going to do? We are going to do a 45-degree rotation. It has gone the different side. Trim everything. So I have also shown you transition meshing. You can also use transition meshing to make quartz meshing on the above side and finer meshing on the inside. So you can see there are no poor choice, there are no poor elements. And elements are CAX4 R. Now no optimization, just simply go to the job, create, say Abacus standard. You can use multiprocessor. Although Abacus standard doesn't use multiprocessor, it is basically RAM dependent. Although I have selected 10 core processor. So let's submit. You can also monitor here. So codes are very important if you are doing an Abacus explicit analysis. Any kind of simulation needs more amount of core. So you can do the parallelization of your numerical problem. Yeah, so this is the time step, and this is the first step what we have chosen, that is 0.01, and here it has completed. This shows the attempt, this is the increment. If sometimes it fails and shows there are too many attempts, or here it shows that there are too many attempts and solution does not converge. So what you need, in case if it doesn't converge, you can either choose this damping factor, use this damping. Also you can change values here. You can put one more zero to make to increase more number of steps. Let's see the results. Create output of this file. Go to unique nodal, select RF2 and U2. Now go to operate on this XY data. Now you need to sum all these reaction forces in the upward direction, that is RF2. So select only RF2 data. So this one here is XY data 1 is the sum of all the component. Now clear and combine. So as it is an symmetric analysis, so you need to multiply it by 2 in case of displacement. Save. This is your load displacement. Name it Abacus standard. So this is your load displacement diagram. Now we will do an Abacus explicit analysis. Copy this model. You can also do on the same, but it will remove all the settings you have done. So first delete the general step, create explicit, first keep it 0.01, keep it 100. So it will give you field output at evenly spaced time interval. That means it will give you 100 data. So here there is no need to change here. In the incrementation you need to change the time period, and sometimes you also need to do a mass scaling in case of quasistatic analysis such as tensile. Loading, you see that although we have copied all the section, but there is no displacement boundary because we have changed the step. So this is here is the most important. Whenever we give a boundary condition, we need to give an amplitude. Most of the time we use a smooth step. You can also change according to your need if there is any. We will keep it a smooth step. That means it will gradually start increasing boundaries and then gradually ends. So time 0, amplitude 0. When time is what we have selected 0.01, amplitude will be 1. 1 times amplitude means 2.5 boundary condition will reach at 0.01 time step. So whenever we change the time step, we need to make sure that we have defined our amplitude according to the time step. No messing, we have already created. Just make it explicit, although there is no need because it will already select or do explicit analysis once we have selected our step. Keep everything default. Abacus, explicit. Here it is. The higher the number of processor, higher will be the speed. So my laptop has 8 core. So that means it has 16 logical processor. So I can go up to 16, but doing 16 will slow down the processor or throttle the processor. So we need to make sure that it is in optimum range. That I have 16 logical processors, so I have chosen 12 according to multiple trials, that which what numbers is giving me a better results. Here you can also do 8 according to your cores, but that will, so you will not be using your full potential of your processor. Whenever you do a explicit analysis, choose this. Now submit. It has a different type of calculation scheme. Always check the warning. What is it saying? So warning is, it is showing warning because we have chosen boundary type element, so that is why it is warning us, because there should be no jumps and jerks in the solution when we choose boundary type. It is not a smooth step by step transformation. So choosing the time step for your Abacus explicit analysis is very important. It is dependent on your lowest element size. There are other videos on the YouTube which will show you better how to choose this time step. It is basically dependent on the natural frequency of your structure. So we take it 4 to 5 times higher than the natural frequency time. So we are basically doing here is a kind of trial and error. We will see its history output, whether any energy of the system is exceeded or not. We will see about when the calculation is completed. So Abacus standard is your stable solution, and explicit is your conditionally stable solution, as I have told you. So you need to cross check all the time, because it may change according to your conditions, like the time step and mass scaling. So what is mass scaling? Mass scaling is, it changes your weight of the system to reduce the calculation time. As you can see, it is using 84% capacity of my processor. I will kill this simulation and restart it again. It is taking longer. We will give a mass scaling of factor 100. It will reduce the incrementation time. So time step will reduce. So as you can see, this is the kinetic energy, which is 304, which is very high, because we have given a mass scaling of 100. That is why kinetic energy is very high. So in case of quasi-static analysis, kinetic energy should be very, very low. There should be no inertial effect. So now the analysis has completed. Let's see the results. Check here the history, output, internal energy versus kinetic energy. Go to the plot. So this one here is your kinetic energy, and this is your internal energy of the system. So this means this is an quasi-static analysis. This is only for cross-checking. It doesn't mean your answer is absolutely correct. It is only a cross-check for there are also other aspects which you should check. Like, what is the state of your system? It should be similar to your experimental data. Combine with. So here most of the time I choose U2, and it shows the displacement of all the nodes. You can select any one node, because these are all the same. So yeah, I choose both of them at one time, because it is easier. We will see side by side how explicit have resulted. So you can see this is more or less, these are very similar. So this is how you can calculate using Abacus Explicit or Abacus Standard. So Abacus Explicit are more useful when we are using higher models, whereas standard analysis is basically used for which are more stable in nature. So Abacus standard are also used in strain rate dependent data. For example, if we are using property, let's say if we are using, in my case I mostly use porous plasticity model. This only works with Abacus plasticity if I use porous failure criteria. So this is the basic difference between the Abacus Explicit and Standard, that Explicit can handle larger models. That is why it is also conditionally unstable, but it is more efficient if we are using larger models, and Abacus Standard has not been capable for the larger models. So you should not, this is only a presentation for how to use Explicit and Standard. You should not see these data may not be correct in case of Abacus Explicit. So you need to cross check with your stress strain gradient. Okay, thank you.